Alright guys, so another short video, but this time we're going to be applying things like structure, bonding and intermolecular forces to these questions to understand how these compounds have properties like high melting points or electrical conductivity. I'm going to recap a few things for you and I am going to give you some help, but for the most part it's going to be a short video and I need you to complete these tasks. I also appreciate that there's not many lines here, so you're going to have to write kind of small, I'm sorry. So melting points, trends of period 3. This is something they can ask you and it could come up as a 3 to 4 marker depending on the way they word the question. What we need to understand is, first of all, across period 3, how do these things exist? So what we've got over here, I'm not going to look at any of this table yet, I'm just looking down here. So from sodium, magnesium, aluminium, this is the left-hand side of our periodic table. You can flip the back of your paper. Just turn over your booklet. There's your periodic table, like down, group 3. Yep. So period 3, we've got sodium, magnesium, aluminium. This is on the left-hand side. These are metals. Then we go to group 4, so we do that big jump over that D block. And then you can see silicon in group 4. This is just below carbon. And then next to that, we have phosphorus, sulfur, chlorine, and argon. So that's all of those elements in that period 3. Sodium, magnesium, aluminium are all metals. They have metallic bonding, giant metallic structures. Therefore, they have a high electrostatic force between positively charged ions and a sea of delocalized negative electrons. That's these guys. Silicon is a giant covalent lattice. Super strong covalent bonds, lots of energy needed to break them. It's a bit like carbon. So carbon's above it. Imagine carbon in like a diamond form. Silicon does something very, very similar. It forms like this diamond form and therefore requires tons of energy to break it. Then we get this massive drop. So you can massive drop down here, but we got phosphorus, sulfur, chlorine, argon. All of these guys are non-metals. They're on the right-hand side of your periodic table. They are non-metals. Something you need to know, you just need to remember this, I'm afraid. Phosphorus naturally exists as P4. So you've got 4 phosphorus atoms all bonded together and they float around together. Sulfur typically exists as S8. So now we have 8 of them atoms all bonded together, all floating around together. Chlorine, you should know, group 7 diatomic. And argon is a noble gas and therefore it just exists on its own. So these are what these molecules are. In order for me to melt these, I need to break the intermolecular forces between them. So going back to the previous video of last week, the intermolecular forces, the bigger the molecule is, the more energy it's going to need to break. Explain why that is the case. That's what we're going to be looking at. So you can see the different sizes of the molecules here due to the size of how many things are bonded to it. And you can see obviously argon will be the smallest of those lot. So I'm not going to read this information, you can read this, but the task that I've asked you to do is to explain the melting point between sodium and aluminium. So firstly, I want you to state, so step 1, which is greater, sodium or aluminium? Why is it greater? You can use location cards for this. It does work and it might make your life a bit easier. And then ultimately, if it's got a higher melting point, what does that mean about the energy required? There's your third mark. Next question, explain the difference in melting points between phosphorus and sulfur. Simple covalent molecules. What's the only thing that's keeping those things together? Why is one greater than the other? And then lastly, explain the difference in melting point between chlorine and argon. What's the only thing keeping those together? And that's all I've got for you for that bit. Let's move on to electrical conductivity. So again, it comes down to the structure and how these things exist. So sodium, magnesium, aluminium, metals, you can find it as a block of metal. Why does that conduct electricity? Why does aluminium conduct more electricity than sodium? Think about what's happening in that metallic structure. So look at aluminium. If you want, you can draw the metallic bonding for aluminium, draw the metallic bonding for sodium. You can do that here. And that'll give you a picture for why you think aluminium will have a better electrical conductivity. Silicon, I will tell you right now, is a bit of an odd one. It is a semiconductor, so it's not a good conductor and it's not, or a good insulator. It's kind of somewhere in between. It's a bit of a weird one, but we just need to know it's a semiconductor. That's as far as you guys will ever need to know. And then lastly, phosphorus, sulfur, chlorine, and argon don't conduct electricity. Can you tell me what is the difference between these and this? And then finally, why doesn't it conduct electricity? Why don't any of those conduct electricity? That's as simple as it is. Enjoy, guys.